Hello and welcome to another video. This week's video is inspired by this very fashionable and stylish shirt that I'm wearing here. I bought this shirt at a place called CERN in Switzerland, where they have built a machine that smashes protons together to study the fundamental structure of matter. And this picture on my shirt is a graphical representation of a collision of two streams of protons. So protons are one of the building blocks of atoms, and as you probably know, atoms make up everything around us. So one question that kind of sprung to mind was, well, if protons are inside everything, how big are protons? We know they're quite small, but just how small are they? So to answer that question, we're going to start with this glass of water. So you probably know that water molecules are made up of hydrogen atoms and oxygen atoms, H2O. And by putting those together, we can work out that 1 mole of water, which is a chemistry term, is a mass of approximately 18 grams. So if I mass out 18 grams of water, that will be 1 mole, and we can start from there. Zero the scale. Let's do, what's that? That's 14, a bit more. 17, 18. Okay, so this little glass here contains about 18 grams worth of water. As you can see, it's not very much. But this is 1 mole of water, which means that in that glass there are Avogadro's number, roughly, of water molecules. I'm a bit thirsty, so I'm going to drink the rest of the water. Okay, so as we said, this is about 18 grams of water. So that means it's about 1 mole. And what that means is that it's Avogadro's number, which is roughly, let's say roughly 6 times 10 to the 23 molecules of water in that glass, in that tiny little glass. So what does 6 times 10 to the 23 mean? Well, it's a 6 followed by 23 zeros. So that's 6, 0, 0, 0, 0, 0, 0, 0 molecules. And to give you an idea of how many that is, if you look up at the night sky, you'll see around 5,000 stars. Those are the ones that are visible to the naked eye. In the whole galaxy, in the whole Milky Way, there are somewhere around 10 to the 11 stars. 10 to the power of 11, which would be about, a few 100 billion, sorry. In the entire observable universe, there are roughly this many stars. So if you take roughly the number of stars in the entire observable universe is the same number of water molecules that are in this tiny little glass of water here. Okay, and if we zoomed in on this little glass of water, and we zoomed in and we zoomed in and we kept going, what we would eventually see is a whole bunch of water molecules. Well, we wouldn't see them because they're not visible to the naked eye, but if they were, and a water molecule is an oxygen atom and 2 hydrogens, arranged something like that. And we're going to zoom in on this hydrogen, because the hydrogen is the simplest atom to consider, because the hydrogen atom is just a proton with an electron orbiting around it. So what are the sizes here? Well, the size of the hydrogen, the whole atom, this kind of total size here, the radius of that is roughly the Bohr radius. It's a bit difficult to talk about exact sizes on this scale, but the Bohr radius is about, let's say, 5 times 10 to the minus 11 meters. And the radius of the proton in the middle there, which is what we were interested in, how small is a proton, the radius of that proton is actually not exactly known at the moment. People are still working on this, but the latest estimates put it around 8 point something times 10 to the minus 16 meters. So physicists would say there's a difference of 5 orders of magnitude between these two sizes, the size of the atom and the size of the proton. And that means the difference in these exponents here is 5. So what that means is that the proton is, what would it be, 10 to the 5, 100,000 times smaller than the whole atom itself. Well, I wanted to put that into a bit of context, and so I thought, well, let me draw an atom the size of this page and then see how small I would need to make the proton in order for it to be to scale. And when I worked it out, unfortunately, that isn't going to work because the proton would not be visible to the naked eye. So I thought, let's work the other way. So I raided the kitchen again, and I found this little pot of cake delights, and in particular these little hundreds and thousands. If I take one of these with a pair of tweezers, because they're a bit small, okay, I've got one. There we go, there's one of those. And I've measured one of these little guys, and it's about a little bit less than a millimeter, the radius of this thing, a bit less than a millimeter. So if we say, it's running away. If we say that this thing has a radius of about 1 millimeter, let's say, just to really be approximate and get close to this, this would be kind of roughly 8, if we're making 8 times 10 to the minus 4 meters. Then, if that's the proton, the atom would need to be about 50 meters in radius. Now that's obviously too big for me to draw, but let's get an idea of what 50 meters looks like. Well, 50 meters is about the radius of a Olympic athletics track. If you think about the athletics track, that looks something like this, and the straight is 100 meters long, then half of that, so the radius of the track, is about, let's say, 50 meters, to a reasonable approximation. So if we wanted to see what a hydrogen atom would look like to scale, we could take this little guy here, this hundreds and thousands piece, this tiny, tiny little thing, and we could put it in the middle of the Cape Town Stadium. And we would see roughly that that's a hydrogen atom to scale, where the little hundreds and thousands piece is the proton. So to answer the question, how small is a proton, the answer is very, very, very small. It's 100,000 in the middle of a stadium, and if you take those and you take 6 times 10 to the 23, this huge number, or multiplied by 2 of course, of these stadiums, and add in an oxygen atom which is even bigger on this scale, then you have this glass of water. So isn't that incredible? This one tiny little glass of water has that many protons in it, and each of those protons is such a tiny, tiny proportion of the size of the atoms. And of course it's the protons that make up the mass of the hydrogen atom. So together with neutrons, which are, I guess, let's say roughly the same size, almost all of the mass of this water, all of those 18 grams, is made up of that one hundreds and thousands piece in the middle of a stadium. Incredible stuff. So I hope you appreciate, after seeing that, how amazing this place is, this place CERN, where they manage these protons, they accelerate these protons, and they take pictures like this of collisions of these tiny, unbelievably tiny little objects. I actually went to a place at CERN called the antimatter factory, where they can control, they can trap antiprotons, which is the antimatter version of protons. So let's say they're roughly the same size as what we've just been talking about, and they can actually get down to counting individual antiprotons, which is absolutely mind-blowing that that's possible with modern technology and science. So hit like, hit subscribe, watch some of my other videos here if you would like, and I'll see you next week for another Sunday snippet of interesting maths and physics.